This is 5.43. This is conditional density. So the idea is that as of now, we've discussed two things. Right? So one is F, or three things. F is the joint density of X and Y. So X and Y are two continuous random variables. F joint density of X and Y. F sub X is the module density of X and Y. What's happened now? Is the module density of X. F sub Y is the module density of Y. And so one thing we observed is independence is equivalent to the fact that the joint density at a point A comma B is the same as the product of the two individual module densities. This is the idea of independence. Whereas, so now what I want to observe is the following: that what if they are not independent? Suppose I know them. Then I know X depends on Y. Suppose you have an event A. So we have an event A. A is an event. And A somehow, let's say, then we have already seen before that, and probability of A is positive, that is A happens. Then we've already seen this formal idea, that is if I let Q of B for any event B, in B, Q of X in B, given the event A, we know how to do this. So sorry, I'll call this probability of X in B given A. I'll define this as Q of X in B. Define this. So this we've already seen before is kind of, in the discrete case, is just the conditional distribution or the conditional probabilities of X given the event. Now this is true in this in this setting. That is we see. Now let's say I'm in above setting. F is the joint density of F is given by capital F. Joint density of X and Y is given capital F, and I have this marginals Fx and Fy. So now let's say I take an event A. Suppose I take an event A. Suppose in the above case. So in the above case, say the event A was the event Y equal to, for some B. So now first you can say that, okay, now you can observe quickly Y is continuous. So probability of A is 0, because we know that any continuous random variable will not assume a single specific value. But suppose I tell you a priori, suppose I give you also, suppose I tell you somehow the F sub Y at the point B is positive. Suppose I tell you that. Suppose this is given. That means the density function is positive, right? The minus given. So what can this What does this imply? Suppose I tell you density is positive. What is the implication of this? Implication of this in, let's say I want a chance that, let's say, x is in the interval, let's say 3, 4, given y is equal to 2. Can I somehow define this idea? That is, I have a probability event 0, but can I somehow define this probability that x is in 3, 4, given that y is equal to 2? Is this a possibility? So I will do some heuristics. Here in green. Let me do a heuristic operation. So I know I'm in this situation now. I know my density of x, y is f, marginal is f sub x, and marginal of y is f sub y. So I'm in that situation. I'm also given f sub y at the point B is positive. So now, so here's the first observation. The first observation is that, so there is maybe I'll do this next page. So let's see what it is. Across, go back up. Let me just start again. Oops, sorry about that. So first is now, I'm given B in R, f sub y at B is positive. Okay, I'm given. Okay. So now this is a simple exercise in calculus that there will be an n in n, and let's say f sub y also is continuous. Okay, f sub y is continuous. And such that there will be an n such that f sub y at the point when it's green, f sub y at the point y is strictly positive for all y in the interval, let's say, for all y in the interval b minus 1 over n to b plus 1 over n. That is, if f sub y of b is positive and f sub y is continuous, then I can find a small region around which this guy will be positive. Now I do the following. So once I have this, then now I observe that this will immediately imply the following idea. That is, the probability that y is in the interval b minus 1 over n to b plus 1 over n, this interval, which is just the integral of the density function between b plus 1 over n to b of f sub y at y dy. If f is positive, this whole thing is going to be positive. That's one observation. Once you have this, that the event is positive, then I can actually define that in the event A, let me call it A sub n, A super n, as the event of y, let's say of the event y is in b minus 1 over n is less than y is less than b plus 1 over n, has a probability of A super n is positive. This. So now I can talk of the conditional probability the way I want to talk about it. So it means, so probability of x is in the interval 3, 4, given the event A super n is well defined. Right? That I know. This, what do I do? I write this as the probability of x in the interval 3, 4, and the event A super n, the whole thing divided by the probability of A super n. That's easy. That's just by conditional probability. But what is that going to be that is going to be the same as the chance. So what is that? A super n is the same as, let me write it down. So let me write this whole thing down so that's clear. So it's it's probability of x in 3, 4. And this event here, A is just this event. So I'll just copy this and put double, duplicate it. Let's put it right here. That's A sub n, right? And divided by the probability of A sub n, which is the same as, and duplicate this again. And that's exactly what I have. So let me, since I'm consistent, let me make the everybody in red, the n in red. So this is a very well precise calculation. Because in A sub n, the whole thing is well defined in this way. And now I know this also is well defined. Right? Because I know how to do it. This is just the same as I write this as the integral from 3 to 4, right? In green, and then divide by, and then I have a dx on outside. And let's say I call it dx on outside. And inside, what will I have? I'll have the integral from b minus 1 over n to b plus 1 over n, right? Of f at the point x comma y. I have a dy first. We have the y in. Let me go back. Sorry about that. We have the y in red. dy, and I have an x. And the whole thing I divide by this top guy. Top guy is exactly what I have below, right? So I have exactly this thing. So the probability of this is just going to be the density of y. So I'll write this as integral from red, so that it's clear. Integral b minus 1 over n to b plus 1 over n. I have a dy, but here I can just put the density of y. So now this is now I'm in calculus regime now. So now what I do is, so these are two calculations I've had so far. Let's go back and check. So the first calculation I did was that, okay, probability of y equal to b is 0. So then I go and do this. I just say, okay, fine. I'm going to just look at an interval around b and stabilize my calculation. Now what happens as n goes to infinity? Let's do that. So now as n goes to infinity, what happens? So n goes to infinity, we know that first thing observed is that A super n, which is the event, let's say, of, I'll leave this in n, so b minus 1 over n is less than y, in green, that's less than y, is less than, let's say, less than b plus 1 over n, right? So this event will converge to the event y equal to b, right? That's clear. To 0, which is our event A. That's the first observation. The next observation is that these integrals, if you look at the integrals, right, you can check in calculus that, let's say I have two integrals right here. So let me do the first one. Let me duplicate that. Let me put that down here. Down here. So here, if I divide by 1 over 2n, or if I multiply by 2n, the area is 2n. So multiply by 2n, this will converge to f sub y at the point. So you have them in green. So this converges to f sub y at the point. That's what the bottom guy is. And if I look at the top guy, right here, if I duplicate this person, when we come down, right here, again the same way. So multiply this by 2n, sorry, this is 2n, 2n, sorry, multiply this by 2n, this person will also converge to f sub x at the point B. That's just calculus. As it all happens and goes. So now if I use these three facts in the top guy, I can normalize both top and bottom by 2n. And what do I get? I get, if I think of this is something I have not made rigorous, but something I can think of this, that the probability, let me go back in green now. The probability, the probability of the event x is in the event 3, 4, given the event y equal to b. Okay. So this I will think of as the limit as n tends to infinity of the probability that x is in 3, 4 and the chance that y is in an, that is b minus 1 over n is less than y is less than b plus 1. Let me put this down. That's what this is, right? Now, this we have figured out from the top calculation is the same as a limit as n tends to infinity of what have we figured out. Let's go back up. Let's take this. This is what we calculate the probability to be. Let me duplicate this guy. Let me bring that down. Oh no. What happened to this? It's right here. So exactly this limit. This limit is what we are calculating. But that we know from this top calculation right here, if I multiply an goes to a, that's okay. And if I do 2n and 2n, if I multiply this by 2n and 2n, so I just multiply this by 2n and multiply this by 2n, same thing. And this we know from the top is the same as, what do we get? We get integral from 3 to 4. The top person goes to f at the point x comma b. I'll write b. B is right in blue. Dx. So dx is again in green. Let's say dx. And the bottom person just goes to fy and b. Fy. So then this it's a little bit, let's just take a little bit, just 3 to 4. F at the point x comma b. So what I use the word b for b is the same as green. So let me just change this as blue. Y is equal to b. Whenever b is, I put a blue. So here the b hangs around. Do like this. B. So fx comma b divided by f sub y at the point b. And I will do this. So it's kind of an interesting calculation. So let me just recap a little bit. Let me just go back and do a double screen. Split view, come back again. So let me come back a little bit. Let's go back up. This guy right here. So the first was that I had an event y equal to b. Its probability was 0. But somehow, let's say I know that the density function is positive at that point. So f sub y at b was positive. Now, how do I now use this information to compute the chance that x is in 3, 4 given y equal to b? I can't use the conventional way because that will involve that I need probability of a to be positive. But I can't do that. So I have to do it in a little clever way. So what you do is you first use calculus. You observe that if fyb is positive and fy is continuous, then you can find an interval around b for which fy is strictly positive. Once you do that, you know the chance of y in this interval is going to be the same as the integral of f sub y on the interval, and that's going to be positive because the function is strictly positive inside of it. It does depend on n, but it's strictly positive. But once you do that, you can go the conventional way. Let's say x in 3, 4 given an is same as x in 3, 4 and an divided by this. And that, if you work out, is exactly going to be this probability by this probability. The top one is given by the joint density, the bottom one given by the minus. Let's keep the right hand side there. Let's move the left hand side down. But once you have that, you have three key things to observe. One is an goes to a, and the two integrals, if I normalize by the area, will go to f sub b. So these are both calculus results. So this I think this is something that this is kind of intuitively obvious, but these are things that you have to sort of understand. Once you do that, you're on your business. Then you know that if you think of the y equal to b as a limiting event, then you can define the conditional probability of x in 3, 4 given y equal to b by this expression. Very nice. Let me stop the view, go back. So now let me sort of sum up everything. So now, if you share a little bit, that the inside guy has some meaning, right? It's the kind of density function of x given y. So that's the next part. I'll define this whole thing. So here's definition. Let's call this 5.4.1. 11. I'll say let x and y be random variables. Having joint density f. Joint density f. You let you let the module density of x of y of y be f sub y at the point. Now you take a crucial fact. Suppose b is a real number such that f sub y at the point b is positive. So I take that point. I have this. Very nice. And let's say f sub y is continuous at b. I take this. So then, so let's say I have these two facts. Then the conditional density is crucial. Conditional density of x given y equal to b is given by f sub x condition on y equal to b at the point x is going to be equal to f at x, come on, the way I observed, at the point b, and this is y equal to b, same as f at the point b, and f sub y at the point for all real numbers x. So similarly, you can define the conditional density of y given x equal to b, but this is broadly the idea. That is, if you have two random variables with joint density f, then the conditional density is going to be given by the ratio of the joint density divided by the mod density, provided the f sub y at the point b was positive. If that's not the case, then you can't do this calculation. So similarly, I'll write down similarly. Suppose f sub x was the marginal density of x was such that f sub x at the point A was positive and f sub x was continuous at A. Then the conditional density, so it's symmetric argument, the conditional density of y given x equal to A is given by, in the same way, you write down as f sub y given x equal to A at the point y is going to be equal to f at the point y, the whole thing divided by the density. So x equal to A, I have A here, and I have f sub x. And this is true for all real numbers. So that's sort of the key sort of arguments that I wanted to present today, in the sense that the conditional density kind of, if you have a density function which is positive at a point and it's continuous at a point, then one can sort of define these probabilities. And once you have these two things, then it's kind of easy to see the following. Last line, I'll just say and I'll stop, is the following that, so either, so from these two things, you could have the chance that x is in an event A, given y is equal to, let's say y equal to b, will just be the integral of the set A on the conditional density, that is f of x given y equal to b at the point x and dx. And similarly, if you want to do probability of y is an event, let's say b, given x is equal to A, that's the same as the integral over b of f of y given x equal to A over y.